For the second unit of thermodynamics, in previous lecture we discussed Carnot's theorem, second law of thermodynamics, the concept of entropy and entropy as a state function, units of entropy, the inequality of clashes and factors affecting entropy. Today we are going to discuss the thermodynamic temperature scale, the entropy change of ideal gases when temperature and volume are variables, the entropy change of ideal gases when pressure and temperature are variables, and the entropy change of ideal gases in isothermal, isobaric and isochoric processes. At first, let us discuss the thermodynamic temperature scale. The principle of Clausius may be rephrased as heat never flows spontaneously, that is, without the expenditure of work from a colder to a hotter body. This statement contains essentially the definition of temperature. You must recall that the concept of temperature was first given on the basis of results of the observations that all bodies reach the state of thermal equilibrium. Lord Kelvin was first to introduce the concept of thermodynamic temperature scale, which is independent of any thermometric substance. To see this, consider the situation shown in figure, which has three reversible cycles A, B and C. There is a high temperature heat reservoir at temperature T1 and a low temperature heat reservoir at temperature T3. For any two temperatures T1 and T2, the ratio of heat absorbed to that of heat rejected remains same for all the Carnot's cycle if temperatures remains same. Now we choose the cycles so as Q1 is same for A and C and Q3 is same for B and C. Now you know that efficiency of Carnot cycle, which is represented by eta, is equal to 1 plus heat at lower temperature divided by heat at higher temperature, which is a function of lower temperature and higher temperature. Here lower temperature is represented by TL and higher temperature is represented by TH. You can see that eta, that is efficiency, is only function of temperature. Also you know that Q1 divided by Q2 will be a function of T1 and T2. Similarly, Q2 divided by Q3 will be a function of T2 and T3, and also Q1 divided by Q3 will be a function of T1 and T3. But Q1 divided by Q3 will be equal to Q1 divided by Q2 multiplied by Q2 divided by Q3. Now you know that Q1 divided by Q2 is a function of T1 and T2 and Q2 divided by Q3 is a function of T2 and T3. If we put all these values, we will get function of T1 and T3 equal to function of T1 and T2 multiplied by function of T2 and T3. Now you know that left hand side, that is Q1 upon Q3, which is a function of T1 and T3, is not a function of T2. Hence, right hand side, that is Q1 upon Q2 multiplied by Q2 upon Q3 cannot be a function of T2. We thus conclude that function of T1 and T2 has the form function of T1 divided by function of T2, and similarly we can say that function of T2 and T3 is equal to function of T2 divided by function of T3. The ratio of heat exchanged is Q1 divided by Q3, which is a function of T1 and T3, and it is also equal to function of T1 divided by function of T3. In general, we can say Q at higher temperature divided by Q at lower temperature is equal to function of higher temperature divided by function of lower temperature. You can see that ratio of heat exchanged is equal to ratio of temperature. So, we can choose any function which is monotonic, and the simplest choice is function of temperature is equal to T itself, and this is thermodynamic scale of temperature. You have seen that QH divided by QL is equal to TH divided by TL. Here QH is the heat absorbed at higher temperature TH and QL is the heat released at lower temperature TL. Lord Kelvin decided to use this equation as the basis of thermodynamic temperature scale. This is the ratio of heat absorbed at higher temperature to that of heat released at lower temperature. The temperature defined in this manner is equal to the temperature defined for ideal gases. Hence, the thermodynamic temperature scale is equivalent to the ideal gas scale. Now, we are going to discuss the entropy change for ideal gases. You know that entropy is a state function, and the value of entropy change depends upon two variables from pressure, volume and temperature. First, we are going to discuss the entropy change when temperature and volume are variables. Let us consider n moles of an ideal gas at temperature T occupying a volume V on pressure P. If this gas absorbs the amount of heat which is equal to dq reversible, then entropy change, that is ds, will be equal to dq reversible divided by T. According to the first law of thermodynamics, dq reversible will be equal to dE plus PdV. Putting in the equation ds equal to dq reversible upon T, we will get ds equal to dE plus PdV divided by T. Now, we know that for an ideal gas, PV is equal to nRT, or we can say that P is equal to nRT divided by V. Here P is the pressure of the gas, N is number of moles of the gas, V is volume occupied by the gas, T is absolute temperature, and R is the universal gas constant. You also know that dE is equal to nCV dt. Here Cv is the molar heat capacity of the gas at constant volume. Substituting this value in the equation, ds is equal to dE plus PdV divided by T, we will have ds equal to nCV dt plus nRT divided by V dV divided by absolute temperature, that is T. Or we can say that ds is equal to n Cv dt divided by T plus nR dV divided by V. Now, integrating between the limits S1, S2, T1, T2 and V1, V2, we will have integral of ds within the limits S1 and S2 equal to integral of n Cv dt divided by T within the limits T1 and T2 plus integral of nR dV divided by V within the limits V1 and V2, or we can say that delta S, which is equal to S2 minus S1, is equal to n Cv natural log T2 divided by T1 plus nR natural log V2 divided by V1, or we can say that delta S is equal to 2.303 n Cv log of T2 divided by T1 plus 2.303 nR log of V2 divided by V1. For 1 mole of an ideal gas, n will be equal to 1 and we will get delta S equal to 2.303 Cv log of T2 divided by T1 plus 2.303 R log of V2 divided by V1. Now, we will discuss the entropy change of an ideal gas when pressure and temperature are variables. Let P1 is the initial pressure of the gas, P2 is the final pressure of the gas, T1 is initial temperature and T2 is the final temperature. V1 is the initial volume and V2 is the final volume. Now, you know for constant amount of the gas, P1 V1 upon T1 will be equal to P2 V2 divided by T2. From this equation, we can have a value for V2 divided by V1, which is equal to P1 T2 divided by P2 T1. Now, putting this value of V2 divided by V1 in the equation, delta S equal to n Cv natural log T2 divided by T1 plus nR natural log V2 divided by V1. We will have delta S equal to n Cv natural log T2 divided by T1 plus nR natural log P1 T2 divided by P2 T1. This will be equal to n Cv natural log T2 divided by T1 plus nR natural log T2 divided by T1 plus nR natural log P1 divided by P2, which is equal to n into Cv plus R natural log T2 divided by T1 plus nR natural log P1 divided by P2. Now, you know that Cv plus R is equal to Cp. So, putting this value of Cv plus R in the equation, we will get delta S equal to n Cp natural log T2 divided by T1 plus nR natural log P1 divided by P2. Now, converting natural log into the log of base 10, we will have delta S equal to 2.303 n Cp log of T2 divided by T1 plus 2.303 n R log of P1 divided by P2. For 1 mole of the ideal gas, value of n will be equal to 1. Hence, delta S will be equal to 2.303 Cp log of T2 divided by T1 plus 2.303 R log of P1 divided by P2. From this equation, entropy change can be calculated when the variables are pressure and temperature. Now we are going to discuss some examples when entropy change has to be calculated based on two variables. First one is 1 mole of an ideal monoatomic gas expands reversibly from a volume of 10 decimeter cube and temperature 298 Kelvin to a volume of 20 decimeter cube and temperature 250 Kelvin. Assuming that Cv is equal to 3 upon 2 R, calculate the entropy change for the process. You know that delta S is equal to Cv natural log of T2 upon T1 plus R natural log V2 upon V1. Here T1 and T2 are initial and final temperatures, V1 and V2 are initial and final volumes, and Cv is the molar heat capacity at constant volume. The value of Cv is given to be equal to 3 upon 2 R, which is equal to 1.5 multiplied by 8.314. Here R is taken in the units of joules per Kelvin per mole. Therefore, putting all the values, we will get delta S is equal to 1.5 multiplied by 8.314 multiplied by natural log of 250 divided by 298 plus 8.314 multiplied by natural log of 20 divided by 10. This will be equal to minus 2.19 plus 5.76 joules per Kelvin per mole, which is equal to 3.57 joules per Kelvin per mole. Now we have another example in which the initial and final pressure of the ideal gas are given. 1 mole of an ideal monoatomic gas expands reversibly from a temperature of 25 degrees Celsius and pressure of 1 atmosphere to a temperature of 0 degrees Celsius and pressure of 500 millimeters of mercury. Calculate delta S for the process. Assume that Cv is equal to 3 by 2. You know that delta S is equal to Ncp natural log T2 divided by T1 plus Nr natural log P1 divided by P2. For an ideal gas, Cp minus Cv is equal to R, where Cp is the molar heat capacity at constant pressure, Cv is molar heat capacity at constant volume, and R is universal gas constant. Therefore, we will have Cp equal to Cv plus R. The value of Cv is given in the problem, which is equal to 3 upon 2 R. Therefore, Cp will be equal to 3 by 2 R plus R, which is equal to 5 by 2 R or 2.5 R. Putting the value of R, we will get Cp equal to 2.5 multiplied by 8.314 joule per Kelvin per mole. Putting all the values in the equation, we will have delta S equal to 2.5 multiplied by 8.314 multiplied by natural log 273 divided by 298 plus 8.314 multiplied by natural log of 760 divided by 500. We will get minus 1.82 plus 3.48, which is equal to 1.66 joule per Kelvin per mole. We can also calculate the entropy change for ideal gases for different types of processes. First, we are discussing the isothermal process. For isothermal process, temperature remains constant, hence T1 is equal to T2. Therefore, the equation delta S equal to 2.303 N Cv log T2 upon T1 plus 2.303 Nr log V2 upon V1 and the equation delta S equal to 2.303 N Cp log of T2 divided by T1 plus 2.303 Nr log of P1 divided by P2 reduces to delta S at constant temperature equal to 2.303 Nr log of V2 divided by V1 and delta S at constant temperature equal to 2.303 Nr natural log P1 divided by P2. For isothermal expansion, V2 is greater than V1 or P1 is greater than P2. Therefore, delta S at constant temperature is positive. But for isothermal compression or contraction, V2 is less than V1 or P1 is less than P2. Therefore, delta S at constant temperature is negative. Now, we are going to discuss some examples for the calculation of entropy change at constant temperature. Calculate the entropy change involved in isothermal expansion of 2 moles of a gas from a volume of 5 liters to a volume of 50 liters at 303 Kelvin. Now, using the relationships delta S equal to 2.303 Nr log of V2 divided by V1, we will get delta S equal to 2.303 multiplied by 2 multiplied by 8.314 into log of 50 divided by 5, which is equal to 38.29 joules per Kelvin. In second case, we are taking the example of isobaric process. We can calculate the entropy change of ideal gas in isobaric process also. In isobaric process, P1 is equal to P2. Therefore, the relationship delta S equal to 2.303 N Cp log of T2 divided by T1 plus 2.303 Nr log of P1 divided by P2 reduces to delta S at constant pressure equal to 2.303 N Cp log of T2 divided by T1. Here is an example to understand the calculation of entropy change for an ideal gas in isobaric process. Calculate the change in entropy accompanying the heating of 1 mole of the helium gas from a temperature of 298 Kelvin to a temperature of 1000 Kelvin at constant pressure. Assume that Cv is equal to 3 by 2 R. As you know that for ideal gas, Cp minus Cv is equal to R, hence Cp will be equal to Cv plus R, which is equal to 3 by 2 R plus R equal to 5 by 2 R or 2.5 R. Putting all the values in the equation, delta S equal to Cp natural log T2 divided by T1, we will get 2.5 multiplied by 8.314 natural log of 1000 divided by 298, which is equal to 25.17 joules per Kelvin per mole. In case 3, we are taking the example of isochoric process. We can calculate the entropy change for an ideal gas for isochoric process also. For isochoric process, V1 is equal to V2. Therefore, the equation delta S equal to 2.303 N Cv log of T2 divided by T1 plus 2.303 Nr log of V2 divided by V1 reduces to delta S at constant volume equal to 2.303 N Cv log of T2 divided by T1. Here is an example to calculate the entropy change of ideal gas in isochoric process. 1 mole of an ideal gas is heated from 100 Kelvin to 300 Kelvin. Calculate delta S if the volume is kept constant and assume that Cv is equal to 3 upon 2 R. When volume is kept constant, delta S is equal to Cv natural log T2 divided by T1. Hence, putting all the values, we will get 1.5 multiplied by 8.314 natural log of 300 divided by 100, which is equal to 13.17 joules per Kelvin. In the end, let us revise what we have learnt today. Today, we discussed thermodynamic temperature scale, entropy change of an ideal gas when temperature and volume are variables, entropy change of ideal gas when pressure and temperature are variables, and the entropy change for an ideal gas in